Hi guys, we're going to continue our friction lesson. Um, Earlier in the week we did balanced friction scenarios, dealing with basically if you were sliding that meant you were pushing at a constant speed, or another balanced scenario was pushing something where it was just about to move, where you balance at that moment with static friction. And remember, the two types of friction are static and kinetic. Static is non-sliding friction, kinetic is sliding friction. And what makes up either one of them is the mu for the corresponding kind, static or kinetic. U, called coefficient of friction, times the normal force. And remember, the coefficient of friction, symbolized by mu, the cursive looking U thing, is a unitless value that's usually between 0 and 1 that represents the roughness and smoothness between the two surfaces rubbing together. Alright, so today we're going to move on to unbalanced scenarios. And we'll again use this simulation to show you some examples of it. And actually first today I'm going to flip the notes, and this is on the next page, page 4 I believe of the notes packet. And again, I'm going to do the same thing. There's a blank one posted for you. If you want to write them, fine. If not, I will post the completed version of the notes and examples as well. Now, for this last scenario, we're going to kind of group a few different cases into this scenario all into one, and then break some down in an example and a little bit more. But if we have unbalanced friction, the main thing is that's different mathematically in setting up the formula is that the acceleration is no longer going to be 0. If you recalled our two balanced scenarios we did earlier in the week when we set up Newton's second law, identified the forces, because acceleration is 0 when something's just about to move or moving at constant v, that have essentially told us that the applied force was equal to one of the types of frictional forces, whether it be static in one scenario, kinetic in another. That won't happen anymore, so we can't say we can't say the applied force is balanced with another one of the frictional forces anymore, because acceleration is non-zero, hence an unbalanced scenario. And that shouldn't be surprising, because we're really just telling you part of Newton's second law in a more specific way right now. Remember, objects will only remain at rest or remain in motion, in constant motion, unless acted upon by an unbalanced force, right? So if we do unbalance the force, then we do have acceleration, which is going to make you not at rest or not moving constant anymore, right? So all these ideas go together from day one. All right, so for the time being, there's really 3 probably sub-scenarios you could get into under unbalanced friction, and we're going to kind of take care of them all at once. We could have a scenario, and this is what our example below is going to be like, where maybe now the applied force is bigger, significantly bigger than the kinetic frictional force. And remember, for unbalanced scenarios, we have acceleration, so we are sliding. Static friction is a non-factor. We do not consider it when we know we're in an unbalanced, non-zero acceleration scenario. We are sliding. There's nothing to discuss about static anymore. And of course, we still have weight down and normal force balancing on that axis upward. Alright, so if this happens, in this scenario here, if the applied force, assuming right's positive and left negative, like we typically do, if the applied force is greater than the kinetic frictional force, what we'll end up having is a positive acceleration. But we could also have a situation where we still may have kinetic friction and applied force, but maybe the applied force is small now. It's not pulling. This could be one of those scenarios where maybe you were pulling something for a while and get tired, and all of a sudden your applied force dips and friction takes over. And this is why friction could eventually stop something if you don't apply a force continually make it go. Because we'll have a negative acceleration because friction's winning the tug of war there, kinetic friction is. And we could even have another kind of variation of that, where what if we only have kinetic friction and no applied force? So you might say, well, how's that possible? If I push something and let it go, I will have only kinetic friction on the x-axis. So if you like push your book across the table and let it go, well then it'll eventually stop and there's no applied force after you let it go. So the kinetic frictional force in that one would also cause a negative acceleration, eventually stopping the object, right? So, and we could show some of these on our thing here. So if I place a big applied force on this thing, applied force is way bigger than frictional force. Notice how it accelerates to the right, right? It's a little choppy there, but it did. But watch me let it go. Now let's do it this way. Put that on it, and I let it go. See, there's only frictional force there. So it hits the wall, slowing it down, right? So if I push and let go, there's no more applied force. So be very careful with our problems moving forward. If we slide it and let go, do not include an applied force anymore. Alright, if it's not there, we can't put it there. Alright, let's do this example problem. Example 3, it's just going to take and tweak example 1 that we did on Monday. So it says, what is the acceleration on the 25 kilogram box in example 1 if you doubled the applied force? So the box is 25 kilograms. Now there's some things we could go back to example 1 and still use other than that mass. If you recall in example 1, it was, or if we look back to it, it was a wood box across a wood floor where we had to look up the mu kinetic. We are under kinetic friction here since we're sliding. It would still be 0.2. Remember, that's a unitless value. Why? Because remember, mu is solely dependent on the textures of the two surfaces in contact. So if I change how I'm pushing it by doubling the applied force, that doesn't change the surfaces in contact, so therefore I could reuse the same mu since we're referring to that same situation in example 1. And hold on guys, sorry for the pause there. Sorry, I just didn't flip back to my screen when I was, my writing screen when I was talking there. So let's just back up. So this example says 25 kilograms is the mass from example 1. And like I just said, we could use the same mu value from that example, 0.2, because that's solely dependent on the types of surfaces in contact. Even if I double the applied force, that will not change that. Okay? So moving along, I doubled the applied force. I have to look at the applied force, which we essentially solved for in example 1. And it was 49 newtons, so I double that, so that means I'm now pushing at 98 newtons. So I am pushing an object. It's just not balanced because it's accelerating. And I have to find that acceleration is what it's asking me for. So the free body diagram of the several scenarios we have up there would be best described by this one. Okay, the one I have in red. Because we have an applied force that is now greater than the kinetic frictional force, which leads me to my next thing. The FFK is still 49 newtons. We could transfer that over. Why doesn't that change if I push harder? Because frictional force equals mu k times the normal force, right? Static frictional, or kinetic, excuse me, not static, kinetic frictional force equals mu kinetic times normal force. Well, we already identified that mu k is the same, right? And normal force is the same. It's still the weight equal to the weight of the object, since we're on a flat surface pushing horizontally still. So since it's solely dependent on that, just because I push harder, we could still say that FFK is still 49 newtons, because it's dependent on those things. So now we set up Newton's second law. F net equals ma like always. And it's going to start by looking the same as we did in example 1, because we have applied force minus kinetic frictional force equals ma. Just the big difference now is, in mathematically, is a is not 0 anymore. We have to find a. And it should be pretty easy at this point. Divide each side by m and plug in our sub-equations, Fa. And actually, you know what? Although we could, I'm going to just solve something from scratch. I do know that that's still 49. But let's just pretend that we didn't know that. It will still come about in this formula when I flip this around. Let's pretend I didn't have that old number to look back on. We could just find it right here within the problem, because I'm going to make the same substitution I did before. It's going to be the applied force minus, remember, using these formulas up here, frictional force is mu k times the normal force, and the normal force is mg all over m. Plugging in the numbers, that's 98 minus 0.2 times 25 times 9.8. Sorry, I got cut off there, guys, but that's times 9.8. I'm running out of room on here. Over 25. So I'm going to sneak it in here. I can't expand my screen anymore. That acceleration, when plugging in those numbers, is 1.96 meters per second squared. And it should make sense that it came out positive, because positives to the right, this applied force is winning the tug of war. Okay? So that means the greater pulls in the positive direction, it will cause a positive acceleration of 1.96. That is a 6 there. Ugly 6, but it's a 6 meters per second squared. Alright? So just what I said before, get full screen here. From what I said before, this value here alone is 49. We knew that from an earlier problem. If we didn't know that, that's why I just scribbled that out and said, you know, we could just resolve it in this problem. 2 times 25 times, that's a 9.8 right there. Okay? And simply divided by m. So that's a typical unbalanced problem when you have both an applied force and a kinetic frictional force. Okay? Now, that's the only example left in our packet, so I'm going to do like a general setup of one of the other scenarios, which is the scenario right here with letting something go where there's no more applied force. And there's something unique, at least compared to this example that we did, that can happen that I need to show you guys so you're aware of. So I'm going to go to new screen here, and we're just going to go over a general scenario of sliding to a stop with no applied force any longer. So that would be, I'm going to redraw that free body diagram for that scenario that we had on the last page. So there would only be kinetic friction this way, FFK. And of course on this axis, weight and normal force balancing out on that axis. The motion is to the right. Alright, that arrow isn't a force. That's just noting the motion. This would be like me sliding my book and letting it go and letting solely friction take over. Just remember our directions as always. The way it's going, to the right's positive, this way is negative. So if we set up Newton's second law, F net on the x-axis equals ma, the only force we have present is FFK. but it's in the negative direction, so we got to have a minus there, right? That equals ma. It's okay if one force is the total force on that axis. That happens sometimes, all right? Kinetic friction, it's sliding, it's kinetic. Remember, if there were an applied force to the right, it would go right there. It's just like we just wiped out the applied force and just have minus FFK there, right? The minus is important because that still accounts for it being a opposing negative force right there. And now, this is the most important thing. Watch what could happen if I do my sub-equations, like always. Don't forget, the new core equation for FFK is mu k times normal force, and normal force equals weight m times g, right? So I could sub in, because of those facts, like I've been in many problems, UK times normal force, which is mg, equals ma. And notice in a kind of problem, well, just like this and only just like this, mass could cancel out. So you are going to run into some problems that are like this that don't give you mass. Don't panic and think you can't solve it. If it is a problem that you let go and the object slides on its own, mass cancels out. Alright? And then therefore we could solve for any missing piece, UK or A, even if we don't have mass. Now let me flip back to our last example. This got a little messy in here. But right here in our last example was the final equation after right before I plug stuff in. This is a common mistake you should not make. In a problem where there still is an applied force, there's still an applied force right here, right? In a problem where there's still an applied force, you cannot cancel. This is not okay. You can't do this. You can't cancel that mass with that mass. If you don't understand why, you need to review your Algebra 1, okay? In order to cancel by dividing something, the numerator has to have that thing you want to cancel in every term. The numerator is a binomial up here. The applied force is a term, and all this together is a term. Since both terms do not have mass in it, this one does, this one does not, you may not do this. Please be clear on that. It can't happen. So in a problem like this example 3, since there's an applied force still hanging around, you absolutely need mass to solve it. You can't cancel it out. You can't make up your own math. You have to follow the rules of algebra. In this general example, there is no more applied force hanging around, so both terms on each side of the equation have mass in it. That's when it could cancel out. Make sure you're very clear on that. Alright, that's all the new stuff to tell you. I'm going to give you a few more problems. These are all some kind of unbalanced problem. And I'm going to give you a little hint on some of them. So listen up to end today here. It's going to be on page 130. And I'm going to give you numbers 22, 23, 24, and 26. Do not do 25. Okay, don't worry about that. Some hints I'm going to give you. Don't forget that there's always a possibility that you may have to use kinematic equations. Alright, that might come up in one of these hints, okay, in order to maybe find acceleration to use it in Newton's second law. Alright, so be aware of that. Also, a more specific thing, in number 22, just so something isn't unclear, in number 22, there is no applied force. This is like one of those scenarios that we just talked about, that you let something go. but it may not be very clear that that's the way it is. If I worded the problem, I'd be more clear about it. So that's why I'm giving you the hint here. It's a block that was pushed that has been let go. Okay? Think of it that way. No more applied force. It may have been not super clear that that's how you're supposed to think about that. Okay? Any other ones where that might happen that will be more clear. All right? So use the examples in the discussion we went over to try these. Again, give them your best shot. They will be simply graded for completion, like most homework assignments are. And I would like you guys to have these completed for Thursday. And on Thursday, I will hold a live session for anybody who could attend to go over all homework from the week, the balanced ones as well as these ones. If you can't attend, no big deal. I will post the recording of the live session on Thursday. Also, the remainder of the week will change a little bit. I always am posting that general outline to start the week. A change to this one, which is no big deal. It just, I gave you a little extra time than I first had planned on this early friction stuff. So we will not be getting to inclines this week. We will be moving into completing a simulated lab on Friday and possibly starting that Thursday, depending on how long it takes to go over the homework. But there will be no inclines till next week. We'll bring that in next week. Alright guys, so don't forget about the live session on Thursday. Look for the link on with the date and time on Classroom. It'll be posted before that.